Welcome back to our deep dive into the world of number theory. Today we're going to be looking at something a little different, the sigmoid function.
Oh, that's interesting. Yeah, it's not the first thing that springs to mind when you think number theory.
Yeah, you think prime numbers and cryptography.
Exactly.
But the sigmoid function with its Z-shaped curve has applications that go far beyond just abstract math.
Yeah, you sent over some great resources on this, a really fascinating excerpt called History of the Sigmoid Function. And it shows how this simple concept has been used in all sorts of disciplines for centuries.
So let's start with the basics. What exactly is a sigmoid function and what makes it so special?
Well, imagine you're watching a rocket launch.
Okay.
It starts off slowly, then it accelerates rapidly through the atmosphere, and then it kind of levels off as it reaches orbit.
Right.
That's the essence of a sigmoid function. A curve that starts gradually accelerates in the middle and then plateaus.
And it's not just a mathematical curiosity. This shape mirrors patterns that we see all around us in nature, in technology, even in human behavior.
Exactly. Think about the spread of a new technology.
Okay.
It starts slowly adopted by a few early enthusiasts.
Right.
Then as word spreads and the benefits become clear, adoption accelerates rapidly. And then it reaches a saturation point where most of the potential users have already embraced it.
That's a great example. And the sigmoid function gives us a mathematical language to describe and even predict these kinds of phenomena.
Now, it's important to remember that we're not talking about one single curve here. Sigmoid is an umbrella term for a whole family of curves that share this characteristic shape.
Okay.
The specific equation might differ, but the underlying principle is the same.
And that excerpt you mentioned, History of the Sigmoid Function, has some really cool visuals that demonstrate this. It shows things like the Gompertz curve, which is used to model systems that saturate at large values like tumor growth.
And the OG curve, which is used in designing dam spillways to manage water flow.
Wow.
So civil engineering and abstract mathematical functions have something in common.
Yeah, it's fascinating how this seemingly esoteric mathematical concept can have such tangible applications in the real world.
Yeah, and the history of the sigmoid function itself shows how ideas can flow across disciplines, sparking innovation in unexpected ways. The timeline in the History of the Sigmoid Function excerpt is amazing. It traces the concept back centuries before it even had a name. And it wasn't just mathematicians contributing. You had psychologists studying human perception, computer scientists developing early neural networks, even those damn engineers we mentioned.
Wow, so it's kind of just waiting to be discovered, popping up in all these different fields until mathematicians finally came along and gave it a framework.
Yeah, and that framework is what makes the sigmoid so powerful, especially in artificial intelligence. Remember those key properties we talked about, bounded, differentiable with that single inflection point? Those aren't just abstract mathematical terms. They're the keys to the sigmoid's potential in AI.
Okay, I'm curious, how do those mathematical properties translate into real-world applications in artificial intelligence?
Well, think of an artificial neuron as a tiny decision maker.
Right.
It receives input signals and then has to decide whether to fire and send out a signal of its own.
Okay.
And the sigmoid function acts like the neuron's internal thermostat. It determines how sensitive it is to those incoming signals.
So the sigmoid function basically decides how strongly the neuron reacts to the information it receives.
Exactly. And the fact that the sigmoid is differentiable is crucial here.
Okay.
It means we can calculate the slope of the curve at any point. And that tells us how much a small change in the input will affect the neuron's output. That sensitivity is critical for training neural networks.
Okay, that makes sense. But how do we actually train a neural network? I know it involves something called backpropagation, but I've never really understood how that works.
It's actually a really cool concept. Imagine a coach reviewing game footage.
The team just lost, and the coach wants to figure out what went wrong.
Right.
So they analyze the plays, identify the mistakes, and then make adjustments to the game plan for next time. Backpropagation is basically the same process, but for neural networks.
So the network makes a prediction, sees how far off it was, and then uses that information to kind of tweak its settings and improve for next time.
Exactly. And the sigmoid function's differentiability allows us to calculate exactly how much each connection within the network needs to be adjusted to reduce the error. It's like the coach telling each player how to improve their performance.
So these seemingly obscure mathematical properties are what make the sigmoid function so powerful in AI.
Absolutely. It's a great example of how theoretical math can lead to groundbreaking technological advances.
Now, the history of the sigmoid function excerpt hints at some of the challenges and debates surrounding the use of sigmoids in AI. It sounds like it wasn't always smooth sailing. Oh, no, it wasn't. Researchers have experimented with all sorts of different sigmoid functions, looking for the ones that perform best for different tasks. For example, the hyperbolic tangent, another six-shaped curve, was popular for a while because it often led to faster training times.
And there was a time when some researchers were even looking at these hard sigmoids, which weren't even smooth curves.
Yeah,
Why was that?
it was all about computational efficiency.
Oh, okay.
Hard sigmoids could be calculated much faster, which was really important when you were dealing with large neural networks and limited computer power. But as computers got more powerful, we saw a resurgence of those smoother sigmoid functions, like the logistic function and the hyperbolic tangent, because they tended to give more accurate results.
So it's this balance between speed and accuracy, and the type of sigmoid you use depends on the application and the computing power you have available.
Exactly. And it shows there's no one-size-fits-all solution in AI. Even something as basic as choosing an activation function requires careful thought.
And it brings us back to the importance of understanding the underlying mathematics.
Right.
By understanding how these different sigmoid functions work, researchers can make better decisions about which ones will work best for their needs.
Exactly. It's a reminder that even in the age of powerful computers and fancy algorithms, having a strong foundation in math is still essential for driving innovation in AI.
This deep dive into the sigmoid function has been really eye-opening. We've gone from its historical roots to its vital role in the future of AI, and we've only scratched the surface. After a quick break, we'll explore some of the wider implications of this versatile function, looking beyond AI to see how its sigmoid curve continues to influence our understanding of the world. You know, it's amazing we started talking about this abstract mathematical curve, and now we're talking about artificial brains and self-driving cars. It's really incredible.
It really shows the power of mathematical modeling, right? The sigmoid function gives us a way to understand and predict things that grow in that S-shaped pattern.
And it's not just AI either, like we saw with agriculture, audio processing, even civil engineering. What other fields are using this sigmoid function?
Well, one area is statistics,
Okay.
specifically logistic regression. It's used to predict the probability of something happening, like yes or no, true or false, based on a set of inputs.
So like if you were trying to predict whether a customer will click on an ad based on their browsing history
Yeah.
and demographics, logistic regression could help you estimate the probability of that happening.
Exactly. The sigmoid function takes the output of that model, which can be any number, and maps it to a probability between 0 and 1.
So it makes the results easier to understand.
Right. And this shows how the sigmoid connects these abstract mathematical ideas to practical decisions in the real world.
And what about in nature? Does the sigmoid function appear there?
Oh, absolutely. In biochemistry, for example, it's used to model how oxygen binds to hemoglobin in red blood cells.
Wow.
This is essential for transporting oxygen throughout the body.
So even at a microscopic level, the sigmoid function is at work.
Exactly. It's pretty amazing. The same function that helps us design artificial neural networks also helps us understand biological systems.
It's incredible when you think about it. I keep thinking back to that timeline, how this simple concept has popped up in so many different fields over time.
Yeah, it really shows that knowledge is interconnected,
Yeah.
and that innovation often happens when seemingly unrelated fields come together.
It's really been an eye-opening deep dive. The sigmoid function is so versatile, it really highlights the power of math to explain the world around us.
And it makes you wonder what other hidden connections are out there waiting to be discovered.
Exactly. Maybe our listeners will be inspired to explore the sigmoid function themselves and find new applications in their own fields.
That would be great. The sigmoid function with its S-shaped curve shows us that even the most complex things often follow surprisingly simple principles.
Well, thank you for joining us on this exploration of the sigmoid function. Until next time, keep those minds curious and keep an eye out for those S-curves. You never know where they might lead you.